What is the purpose of using directional coupler in microwave communication systems? With the help of schematic diagram, explain the working of a two-hole waveguide direction coupler. The purpose of using direction couplers in microwave communication systems are signal monitoring and power measurement. First one, directional couplers allow for extraction of a small sample of the signal power from the main line without significantly affecting the original signal. This enables monitoring signal strength and characteristics at various points in the microwave unit. Isolation. Direction couplers can provide isolation between different parts of a microwave system. A large portion of the signal traveling in one direction is prevented from passing through to the other direction, prevents unwanted leakages. Balanced mixer design. Direction couplers used in mixers to convert at a signal from one frequency to another. Beam forming in antenna arrays. Direction couplers can be used to control the amplitude and phase distribution of the signals, feeding individuals antenna elements and shapes the radiation pattern. ఎలా వస్తా అంటే ఒక బ్రిడ్జ్ లాగా ఇన్పుట్ పోర్ట్ 1, దాని కరెక్ట్గా ఆపోజిట్లో ట్రాన్స్మిటెడ్ పోర్ట్ P2, దాని కింద ఐసోలేటెడ్ పోర్ట్ P4, దాని పక్కన కపుల్డ్ పోర్ట్ P3. This coupler type has 4 parts and symmetric design, allowing forward and reverse signals to be sampled simultaneously. Coupler factor. This indicates the fraction of the input power at P1 that is delivered to the coupled part P3. Coupling C equal to 10 log 10 P1 by P3. Directivity is the measure of the coupler's ability to separate waves propagating in forward and reverse directions as observed at the coupled P3 and isolated P4 parts. Directivity D equal to 10 log P3 by P4. Isolation, it indicates the power delivered to the uncoupled load P4. Isolation I equal to 10 log P1 by P4. Insertion loss, it is the ratio for the input power Pi delivered to the transmitted power P2 port. Insertion log L equal to 10 log P1 by P2. 10 log P1 by P2. Gain of a pyramidal horn antenna. The gain of a pyramidal horn antenna is defined as the ratio of the radiated power intensity along the beam axis to the intensity of an isotropic antenna with the same mathematically. G equal to n suffix AP. N suffix AP means aperture efficiency into 4 pi a by lambda square. A means area of aperture. G equal to NAP into 4 pi a by lambda square. Beam width of pyramidal non-antenna. A beam width is the angular span of the main lobe of the radiation per horn, which is the region of the pattern where most of the power is radiated. The beam width is measured at the angle between 2 points on either side of main lobe, also known as minus 3 dB point or half power point, where the power radiated drops to half of its maximum value. Now, question for a pyramidal horn antenna, define gain and bandwidth. Okay, if the operating frequency is 10 GHz and a horn antenna has height of 10 centimeters and width of 12 centimeters, calculate the beam width and gain taking the value of k equal to 0.5. So numerical, given data, f equal to 10 GHz, h equal to 10 centimeters, w equal to 12 centimeters, k equal to 0.5. Beam width, vertical beam width theta E equal to 56 lambda by h equal to 56 into c by hf equal to 56 into 3 into 10 cube 10 power 8 by 10 into 10 power minus 2 into 10 into 10 power 9 equal to 16.8 degrees. Horizontal beam width theta h equal to 67 lambda by w equal to 67 c by hf equal to 16.75 degrees. Gain G equal to 0.5 into 4 pi by 0.03 into 120 into 10 power minus 4, that equal to 19.23 dB. 19.23 dB. Next question, 6th law. Here let us 60 MHz uniform plane wave is propagating in a lossless medium with epsilon r equal to 9 and mu r equal to 4. First option. First one, determine the phase constant beta, wavelength lambda and phase velocity Vp for the wave. The answer is given data f equal to 60 MHz, epsilon r equal to 9, mu r equal to 4. First one, beta lambda Vp. Beta equal to omega by c into root over mu r into epsilon r, that can be written as omega of root mu r epsilon r by c. Beta equal to 2 pi into 10 60 into 10 power 6 into 6 by 3 into 10 power 8. Beta equal to 7.54 radians per meter. Beta equal to 2 pi lambda. Lambda equal to 2 pi by beta. that equal 2 pi by 7.54 lambda equal to 0.833 Vp equal to omega by beta Vp equal to 2 pi into 16 to 10 power 6 by 7.54 Vp equal to 5 into 10 power 7 meters per second. Next question. This wave is normally incident onto another medium having conductivity sigma equal to 4 Siemens per meter, epsilon r equal to 80 and mu r equal to 1. The second medium is assumed to be good conductor at 60 megahertz. Determine the fractions of the incident power that are reflected and transmitted. Okay, media gista left side emo lossless dielectric, right side emo good conductor. Lossless dielectric lo m of minus 1 epsilon r equal to 9 mu r equal to 4 m of minus 2 good conductor side the medium 2 ani sigma equal to 4 Siemens per meter, epsilon r equal to 80, mu r equal to 1. So eta 1 equal to 120 pi into root over mu r by epsilon r, that equal to 120 pi into root over 4 by 9, that equal to 80 pi. Eta t equal to eta 2 equal to root over omega mu by sigma at the angle of 45 degrees, that equal to root over 2 pi into 60 into 10 power 6 into 4 pi into 10 power minus 7 by 4 at the angle of 45 degrees. Eta t 2 equal to 10.88 angle of 45 degrees, gamma equal to eta 2 minus eta 1 by eta 2 plus eta 1, 10.88 at the angle of 45 degrees minus 251.32 at the angle of 0 degrees whole by 10.88 at the angle of 45 degrees plus 251.32 at the angle of 0 degrees, that equal to 0.94 angle 176.5 degrees. Tau equal to 1 plus gamma equal to 1 plus 0.94 at the angle of 176.5 degrees, that equals 0.84 at the angle of 42.94 degrees. Now P reflected by P incident equal to minus of gamma square equal to minus of 0.94 whole square equal to minus of 0.8836. P trans by P incident equal to tau square into eta 1 by eta t equal to 0.084 whole square into 80 pi by 10.88, that equals 0.163. 0.163. Write an 8085A program to exchange the higher and lower nibble of 10 8-bit numbers stored from location 2200H. Make use of subroutine and explain parameter passing using point and stack techniques. Solution: given data of 10 bytes from 2200H, required program tends to change higher and lower nibbles of these 10 bytes. Algorithm: initialize memory pointer using HL pair 22200H and SP to F004H considered. Load a count of 10 into register B. Call a subroutine to exchange lower and higher nibbles of byte using rotate left instruction. Repeat the same operation till the 10 bytes are completed. When call instruction is executed, step 1, next instruction address or PC value is pushed onto stack. Step 2, program control is transferred to the subroutine address. After call is that is final value, but before this SP-1 PCH of PCH tends to SP-1, PCL tends to SP-2, SP-2 equal to tends to SP, assigns to SP. When RET return instruction is executed in subroutine, the value at the top of stack, that is 2B, are accessed into PC. The program control is transferred to the 16-bit address that is in PC. SP plus 2 tends to SP. LXI SP comma F004H in brackets initialize stack pointer. LXI H 2200H initialize memory pointer at the rate of 22200H. MVI B comma 0AH count of 10 into register B. Next, call EXNG, call subroutine EXNG. INXHG means increment memory pointer. DCRB means decrement count in B. JNZ next means if Z equal to 0 question mark, then go to next, else halt. HLT means stop. Subroutines for exchanging nibbles. EXNG MVIC, 04H load count of 4 into register C. Move A, M, move data byte in the ACC from memory. RPT, RLC, rotate ACC left for 1 bit without carry to exchange lower and higher nibbles. DCRC, check count in register C by C minus 1. Move M, A, JNZ RPT. If Z equal to 0, then RPT else RET. RET means return to main program. If data byte at the rate of 2200H is 25H, that is 001001012 base 2, then after rotating 4 times to left, it would be 01010010 base 2 52H. CY అలా రొటేషన్ చేస్తే 52H అని వస్తుంది. Now, sixth low C question. That first one, 10 marks. Receiving antenna and input RF amplifier are the most crucial areas of a ground receiver in a satellite communication system. Write a typical block diagram. Considering the receiving only TV, ROTV converter and indicate the various aspects with the typical numerical values of frequencies. The receiving only home TV systems in satellite communication consists of two units. First one indoor unit, second one outdoor unit. First one indoor unit, the single mesh type reflector may be used which focuses the signals into a dual feed horn which has to separate outputs, one for the C band signals and one for the KU band signals. 2. Outdoor unit. This consists of a receiving antenna feeding directly into a low noise amplifier combination. The receiver antenna is a parabolic reflector with downlink frequency band of 12.2 to 12.7 GHz having a range of 500 MHz which accommodates 32 TV or FM channels, each of which is 24 MHz wide. The signal fed to the indoor unit is normally a wideband signal covering the range 950 to 1450 MHz. This is amplified and passed to a tracking filter which selects the desired channel. The selected channel is again down converted to from 950 to 1450 MHz range to a fixed intermediate frequency of 70 MHz. Although VHF range are also used, the EF carrier must be demodulated and the baseband information used to generate a VSB signal which is fed into one of the TV set. So the diagram comes as like this. First you will get a receiving horn and polarizer, LNA, outdoor unit. Next you will get to amplifier, okay na, tracking filter and down converter. For that channel select and display tunable oscillator which is given as tracking filter and down converter. Then from tracking filter and down converter to IF block 70 MHz, then DF demodulate, then AF demodulate, then TV set, then TV set. Next to second question. Highlight the importance of power budget and rise time budget in the design of optical communication systems. What are the three factors that limit the transmission distance when the link lengths are longer or data transmission rates are high? Show how maximum link length is determined for RZ coding and NRZ coding considering material dispersion. So పవర్ బడ్జెట్ టీఎక్స్ ఎల్ఎస్ఎఫ్ కనెక్టర్ ఉంటుంది, స్ప్లైస్ ఉంటుంది, ఆల్ఫా ఇంటూ ఎల్ ఉంటుంది, కనెక్టర్ ఉంటుంది, స్ప్లైస్ ఉంటుంది, ఆర్ఎక్స్ ఉంటుంది. సో ద డిస్టెన్స్ ఈజ్ ఎల్. ఫస్ట్ స్టార్టింగ్ ఈజ్ ఎల్ఎస్ఎఫ్, నెక్స్ట్ ఈజ్ ఎల్ఎఫ్డి. The optical power budget in a fiber optic communication link is the allocation of available optical power among various loss producing mechanisms such as coupling loss, fiber loss, splice loss and character loss to ensure the adequate signal strength at the receiver. The power received is a function of A. Power from light source PT, B. Source to fiber loss LSF, C. Fiber loss depends on length alpha into L, D. Connectors are splicey losses LCA, D. Connector to splice losses LCA, fiber to detector loss LFD. Third one, a system margin is incorporated into optical power budget to allow for component aging, temperature fluctuations and losses arising from components that may be added in future. PR equal to PT minus of LSF plus L splice A plus L connector plus alpha L plus L coupler plus L FD. Rise time budget. A rise time budget analysis is a convenient method for determining the dispersion limitation at an optical link. The purpose of rise time budget is to ensure that the system operates properly at the intended bit rate. The total transmission time degradation T system of digital link should not be exceed 70% of an NRZ bit period or 35% of RZ data. T system equal to root over TFS square plus TRLX square, TR fiber square, TRPD square, TRX square. These are all considered as a suffix. The T system equal to 0.35 by bandwidth. The three factors that limit the transmission distance when the link lengths are long or data rates are high are optical power, loss and dispersion, receiver sensitivity. Modulation formats. There are two modulation formats in digital OFC are NRZ, non-return to 0, second one return to 0. The NRZ signal format displays performance advantages over that NRZ like higher peak power, greater noise immunity and better BER performance. For an RZ impulse format, the bit rate RB equal to B equal to 1 by T, T equal to pulse duration, T system equal to TR equal to 0.35, T equal to 0.35 by B equal to 0.35 by RB. RB equal to 0.35 by T system. For an NRZ pulse format, the bit rate RB equal to B by 2 equal to 1 by 2. The maximum bit rate RB equal to 0.7 by T system. 0.7 by T system. Next, 7th law A. A lossless transmission line of length 0.8 lambda and characteristic impedance Z0 equals 75 ohms operating at 60 megahertz has velocity on the line 3 into 10 power 8 meters per second. If the line is short circuited at the load and find the input impedance Zin at what distance. Once again I will repeat, a lossless transmission line of length 0.8 lambda and characteristic impedance Z0 equals 75 ohms operating at 60 megahertz has velocity on the line 3 into 10 power 8 meters per second. First one, if the line is short circuited at the load and find the input impedance Zin at what distance closest to a short circuited end is the impedance seen 0. Second question, if the short circuit is replaced by a load ZL equals 60 minus J40 ohms, determine the input impedance Zin, reflection coefficient and so on. So first question if the line is short circuited at the load and find the input impedance Zin at what distance closest to the short circuited end is impedance seen 0. Given data, 7th law yellow, given data L equals 0.8 lambda, Z0 equals 75 ohms, F equals 60 into 10 power 6 Hz, V equal to 3 into 10 power 8 meters per second. Z short circuit equal to J Z0 tan beta L equal to J75 tan of 2 pi by lambda into 0.8 lambda equal to J7.5 tan of 1.6 pi, that equal to minus J230.826 ohms. From the graph, impedance will become 0 at lambda by 2 distance. X axis emo 0, lambda by 4, lambda by 2, 3 lambda by 4 L అని రాస్తాం. Y axis లేమో ZS by C అని రాస్తాం. ఓకేనా, పై బై 2 దగ్గర ఓపెన్ సర్క్యూట్, పై దగ్గర షార్ట్ సర్క్యూట్, 3 పై బై 2 దగ్గర ఓపెన్ సర్క్యూట్ అని రాస్తాం. దానికి ఒక పెరాబోలా 0 to OC అని రాస్తాం. ఇక్కడ లాంబ్డా బై 4 టు పై 1, పై 2 అది OC అని గ్రాఫ్ గీస్తాం. L ఈక్వల్ టు లాంబ్డా బై 2 ఈక్వల్ V బై 2F ఈక్వల్ టు 3 into 10 power 8 by 2 into 60 into 10 power 6 equal 2.5 meters. Alternately for Z short circuit equal 0, J Z0 tan beta L equal to 0, tan beta L equal 0, beta L equal to n pi, L equal to n pi by beta, that equal to n pi by 2 pi into lambda, that equal to n lambda by 2. For n equal to 1, L equal to lambda by 2, that equal to 2.5 meters. 2.5 meters. Second question, if the short circuit is replaced by a load ZL equals 60 minus J40 ohms, determine the input impedance Zin, reflection coefficient gamma, and standing wave ratio SWR. Determine the power delivered to the load if a source of 10 volts RMS with series impedance ZG equal to 75 ohms is connected at the input. For Zn gamma comma S, 0.8 lambda is the length of the this one coaxial cable. Load ZL equal 60 minus J40 ohms, beta L equal to 2 pi by lambda into 0.8 lambda equal to 1.6 pi, tan beta L equal to tan of 1.6 pi, that equal to minus 3.078. Zn equal Z0 into ZL plus J Z0 tan beta L by Z0 plus J ZL tan beta L. Zn equals 75 into 60 minus J40 minus J213.826 by 75 plus J16 minus J40 into minus 3.078. Zn equal to 108.975, angle of 27.09 degrees. Gamma equal to ZL minus Z0 by ZL plus Z0, that equals 60 minus J40 minus J75 by 60 minus J40 plus 75, that equals 0.303, angle of minus 94.05 degrees. Gamma equal to 0.303, angle of minus 94.05 degrees. S equal to 1 plus mod gamma by 1 minus mod gamma. S equal to 1.87. Power delivered to the load. Vg is the input. Vg equal to 10 Vrms and rastam. A series with Zg equal to 75 ohms and rastam. PL transmitter and rastam. Okay, now load equal to PL 60 minus J40 ohms and rastam. Okay, now reflection coefficient gamma G, gamma L. PL equal to 1 minus modulus of gamma square into P incident. P incident equal to numerator part V0 plus whole square by denominator part 2 Z0. V0 plus equal to Z0 Vg by Z0 plus Vg. Then pakkana into e power minus j beta L by 1 minus gamma L into lambda G into e power minus j2 beta L. How we can write as V0 plus equal to numerator part Z0 Vg e power minus j beta L whole by denominator part z0 plus zd g into 1 minus gamma l gamma g into e power minus j2 beta l v0 plus equal to 75 into 10 root 2 into e power minus j2 pi by lambda into 0.8 lambda e power minus half j into 2 pi by lambda into 0.8 lambda new అది ఎక్స్పోనెన్షియల్ పార్ట్లో ఉంటుంది హోల్ బై 75 ప్లస్ 75 v0 plus equal to 7.07 that equal to e power minus j 1.65 v0 plus equal to 7.07 angle of minus 288 degrees that equal to minus that equal to 7.07 at the angle of 72 degrees pl equal to ఆ ఫార్ములాలో సబ్స్టిట్యూట్ చేస్తే వస్తుంది 1 minus gamma square into p incident pl equal to 3.026 watt 3.3026 watt. Next question 7th will be 10 marks question. What is essential hazard? Find the hazard free realization circuit for the following function f of a b c d equal to sigma m 1 5 7 14 and 15. Essential hazard will occur in asynchronous sequential circuits is named as essential hazard. This type of hazard is causal by unequal delays along two or more paths that originate from an equivalent input. An excessive delay through an inverter circuit as compared to the delay related to the feedback path may cause such hazard. Essential hazards can't be corrected by adding redundant gates as it is in static hazards. The problem that they impose is often corrected by adjusting the quantity of delay within the affected path to avoid essential hazards. Each feedback circuit must be handled with individual care to make sure that the delay within the feedback path is long enough compared with delays of other signals that originate from the input terminals. The hazard-free realization circuit for the following function f of a, b, c, d equals sigma m of 1, 5, 7, 14, 15. ఎలా రాస్తామంటే a b c d 0001 1110 0001 1110 157 15 అనేది ఒకటి 57 అనేది ఒకటి 75 అనేది ఒకటి 15 14 అనేది ఒకటి. ద హెజార్డ్ ఫ్రీ రియలైజేషన్ ఈజ్ ఎఫ్ ఈక్వల్ ఏ బార్ బీడీ ప్లస్ ఏబీసీ ప్లస్ బీసీడీ ప్లస్ ఏ బార్ సి బార్ డి. 7th C. Suppose that a 1 megahertz channel can support a 1 Mbps transmission rate. The channel is to be shared by 10 stations. Each station receives frames with an exponential inter-arrival rate of lambda equal 500 frames per second and frames are of constant length L equal to 1000 bits. Compare the total frame delay of a system that uses FDMA to a system that uses TDMA. Compare IS54 and GSM in terms of their ability to handle speech and the effect on spectrum efficiency. Given that bandwidth equal to 1 megahertz, RB equal to M1 Mbps, number of stations equal to 10, frame rate lambda equal to 500 frames per second, frame length L equal to 1000 bits, total frame delay equal to how much? FDMA, the total frame delay in FDMA is determined by the transmission time, propagation delay and queuing delay. Transmission time equal frame length by transmission rate that equal to L by RB that equal 1000 by 1 in 10 power 6 that equal 10 power minus 3 equal to 1 millisecond. Transmission time equal to 1 millisecond. Propagation delay equal to 0. Queuing delay equal to 0. Total frame delay in FDMS is 1 millisecond. TDMA, in TDMA each station is allocated a specific time slot to transmit in data. Since there are 10 stations, each station gets 1 by 10th of the total available time. Transmission time equal to frame length by transmission rate that equal to L by RB that equal 1000 by 1 in 10 power 6 that equal 1 millisecond. Transmission time equal to 1 millisecond. Propagation delay equal to 0. Queuing delay equal to 9 milliseconds. Each station will have to wait for its allocated time slot, which introduces an additional delay of 9 milliseconds before it can transit its data for the other 9 stations. Total frame delay in TDMA is 1 millisecond plus 9 milliseconds that equal 10 milliseconds. FDMA has a lower total frame delay compared to TDMA. IS54 offers good efficiency with its 3 user TDMA and pi by 4 DQPSK modulation QPSK. It was the first US digital cellular standard. GSM has a lower efficiency than IS54 due to its 8 user TDMA and GMSK modulation. However, its global compatibility and widespread adoption makes it a significant standard. GSM provides higher bitrate 22.8 kbps to a full rate speech channel than IS54, which only provide 16.2 kbps. IEEE 802.11 silent features are IEEE 802.11 defines wireless local area networks Wi-Fi. It uses a CSMA CA for media access and includes encryption. Wireless networks can operate in ad hoc mode with no base station or infrastructure mode with an access point. Infrastructure networks can connect multiple basic service sets to extend the network. IEEE 802.11 architecture. The components of IEEE 802.11 architecture are as follows. Stations STA. Stations comprises of all devices and equipments that are connected to the wireless LAN. A station can be of two types: wireless access point WAP, are generally wireless routers that from the base stations are access clients. Clients are workstations, computers, laptops, smartphones, etc. Basic service set BSS. A basic service set is a group of stations communicating at the physical layer level. BSS can be of two categories depending upon the mode of operation. Infrastructure BSS, here the devices communicate with other devices through access points. Independent BSS, here the devices communicate in a peer-to-peer basis in an ad hoc manner. Extended service set ESS, it is a set of all connected BSS. Distribution system DS, it connects access points in ESS. Distribution system DS. ESS means BSS AP STA 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 BSS AP STA STA AP BSS STA STA. Okay na. Eighth question A, 8 marks. An air-filled rectangular waveguide has dimensions A equal to 2.4 centimeters and B equal to 1.2 centimeters. Or what range of frequencies will the waveguide operating single mode? At what range of frequencies will this guide operate in single mode? Given data A equal to 2.4 centimeters, B equal to 1.2 centimeters. Single mode of operation, assume dominant mode of operation, that is TE10. Here A greater than B, A equal to B, so order of cutoff frequency FC of TE10 less than FC of TE01 equal to FC of TE20. FC of TE10 equal to C by 2A, that equal 3 into 10 power 10 by 2 into 2.4 equal 6.25 gigahertz. FC of TE01 equal C by 2B, 3 into 10 power 10 by 2 into 1.2, 12.5 gigahertz. Then TE10 6.25, TE01 or TE20 12.5 gigahertz. For single mode of operation, frequency range is 6.25 gigahertz less than 12.5 gigahertz. Next, the 12 marks question. This air-filled waveguide is joined end to end with another waveguide of identical dimension. The second waveguide is filled with a lossless dielectric of relative permittivity epsilon r. Find the maximum allowable value of epsilon r such that single mode operation can be simultaneously ensured in both waveguides. What will be the range of frequencies for single mode operation if epsilon r is chosen to be equal to half of the maximum allowable value? For FC equal to 6.25 gigahertz. Okay na, work side and free space. Next time epsilon r FC equal to C by 2A into root epsilon r. Root epsilon r equal to C by 2A FC. So that equal to 1. Epsilon r equal to 1. For epsilon r equal 0.5. C by 2A root epsilon C numerator 2A pakkana into root over epsilon r under root less than f naught is less than C by 2B epsilon r under root. So 3 into 10 power 10 by 2 into 2.4 into root over 0.5 less than f naught less than 3 into 10 power 10 by 2 into 1.2 into root over 0.5. 8.84 gigahertz less than f naught less than 17.7 gigahertz. 17.7 gigahertz. Next question, 8th B, 14 marks question. In CMOS logic circuit, assume that VDD equal to 1.8 volts, load capacitance CL equal to 0.1 picofarads, LN equal to LP equal to 2 lambda, WN equal to 18 lambda, and WP equal to 42 lambda. Using 0.18 micrometers parameters, Kn dash equal to 96 microamperes per volt square, Kp dash equal to 48 microamperes per volt square, and Vt1 equal to IV top, I equal to 0.4 volt. Find the propagation delays TPHL and TPLH. We have VDD equal to 1.8 volts, CL equal to 0.1 picofarads, Ln equal to LP equal to 2 lambda, WP equal to 42 lambda, Wn equal to 18 lambda, Kn dash equal to 96 microamperes per volt square, Kp dash equal to 48 microamperes per volt square, Vth equal to modulus of Vtp equal to 0.4 volt. The effective transconductance parameters Kn and Kp are given by Kn equal to Kn dash into Wn
by ln, kp equal to kp dash into wp whole by lp. Substituting the values, kn equal to 96 microamperes per volt square into 18 lambda by 2 lambda, that equal to 864 microamperes per volt square. Kp equal to 48 microamperes per volt square into 42 lambda by 2 lambda, that equal to 1008 microamperes per volt square. The propagation delays are given by TPHL equal to 0.69 CL VDD C suffix L V suffix DD by I suffix P. So T suffix PHL equal 0.69 into C suffix L into V suffix DD by IN, where IP and IN are the peak currents for PMOS and NMOS during switching respectively. They are approximately as IN equal to K suffix N by 2 into V suffix DD minus V suffix TN whole square. IP is nearly equal to Kp by 2 into V suffix dd minus modulus of Vtp whole square. Substituting the value In equal to 864 microamperes per volt square by 2 into ఇదంతా ఒక పార్ట్ into 1.8 minus 0.4 whole square. Like that we will calculate IP also. Now using these currents to find the delays, TPHL we will calculate. Next, to high to low propagation delay, TPHL is 0.1258 picosecond. Low to high propagation delay, TPLH is 0.1467 picoseconds. Next, find the jet transform of the following composite signal. Determine the region of conversion. This question is for 6 marks. X of n equal 1 by 2 whole power n, u of n plus 4 into minus 1 by 3 whole power 2n into u of n into u of n. So given signals x of n equal 1 by 2 power n into u of n plus 4 into minus 1 by 3 into whole power 2n into u of n 1 by 2 whole power n into u of n plus 4 into minus of 1 by 3 whole square whole power n into u of n 1 by 2 whole power n into u of n plus 4 into 1 by 9 whole power n u of n. By applying z transform, x of z equal 1 by 1 minus half z inverse plus 4 by 1 minus 1 by 9 z inverse. Note a power n u of n z transform equal to 1 by 1 minus a z inverse mod z greater than a. For existence of z transform, sigma n equal to minus infinity to infinity, x of n e r power minus n modulus is less than should be infinity. So sigma n equal 0 to infinity half power n r power minus n plus 4 into 1 by 9 whole power n into r power minus n less than infinity. Sigma n equal to 0 to infinity 1 by 2 r whole power n plus 4 into 1 by 9 r whole power n less than infinity. Sigma n equal to 0 to infinity 1 by 2 r whole power n plus 4 into sigma n equal to 0 to infinity 1 by 9 r whole power n less than infinity. To satisfy the above condition, 1 by 2 r less than 1 and 1 by 9 r less than 1, r greater than 1 by 2 and r greater than 1 by 9. From equations 1 and 2, r greater than 1 by 2 modulus z greater than 1 by 2. So the region of convergence for the given signal x of n is mod z greater than 1 by 2. 1 by 2. 8th plus C, 10 marks. The main ingredients of a good routing algorithm depend on the objective function that one is trying to optimize. In this background, list and explain the goals that a routing algorithm should seek in general. How are routing algorithms classified, distinguished between linked state routing and distance vector routing? First question, okay, now routing is the process of forwarding of a packet in a network so that it reaches the destination. The main goals of routing are correctness, simplicity, robustness, stability, fairness, optimality. Classification of routing algorithms. Adapting routing algorithms. These algorithms change their routing decisions to reflect changes in the topology and in traffic as well. The optimization parameters are the distance, number of hops and estimated transit time. This can be further classified as follows: centralized, isolated, distributed. Second one, non-adaptive routing algorithms. These algorithms do not base their routing decisions on measurements and estimates of the current traffic and topology. This can be classified as follows: flooding, sequence numbers, hop count, spanning tree. Flooding low brackets, sequence numbers, hop count, spanning tree. B, random walk. 3, delta routing. It is a hybrid of the centralized and isolated routing algorithms. 4, multi-path routing. Instead of single best path, sometimes in order to improve the performance, multi-paths between single pair of nodes are used. 5, hierarchical routing. In this method of routing, the nodes are divided into regions based on hierarchy. Difference between linked state and distance vector routing. Linked state, it is a dynamic routing algorithm which each router shares knowledge of its neighbors with every other router in the network. Linked state, a router sends its information about its neighbors only to all the routers through flooding. Linked state, information sharing takes place only whenever there is a change. Linked state, it makes use of Dijkstra's algorithm. Linked states, heavy traffic due to flooding of packets. Now we will consider distance vector. It is a dynamic vector routing algorithm in which each router computes a distance between itself and each possible destination, that is its immediate neighbors. Distance vector, the router shares its knowledge about the whole network to its neighbors and accordingly updates the table based on its neighbor. Distance vector, the sharing of information with the neighbors takes place at regular intervals. Distance vector makes use of Bellman-Ford algorithm. It counts to infinite problem and loop will be there forever. Next concept is, next question, second question is, what are the applications protocol with respect to TCP? Show schematically how file transfer occurs using FTP. What are the 3 default specifications which must be supported in every FTP implements? That is for 10 marks. That is for 10 marks. The protocols used in application there for TCP are bootstrap protocol, DHCP, dynamic host configuration protocol, DNS, domain name server, FTP, file transfer protocol, telnet, terminal network, SMTP, simple mail transfer protocol, SNMP, simple network management protocol, FTP, file transfer protocol, client, user interface, control process, data transfer process, that is called client. In server you will get control process, data transfer process, there is no user interface. In the middle, TCP IP network, control connection, data transfer connection. It is a standard mechanism provided by TCP IP for copying a file from one host to another. Transferring files from one computer to another is one of the most common tasks in networking. FTP establishes 2 connections between the host. One connection is used for data transfer and another for control information. The data connection use very complex rules and the control connections use simple rules. The user have 3 components: user interface, client process, client data transfer process. The server have 2 components: server control process, data transfer process. 8th one, the control connection remains connected during the entire FTP session and data connection is opened, closed for each file transfer. Hi friends, welcome to my channel. Today's topic is ESC Mains 2024 Part 2. An angle modulated signal has the form U of t equal to 100 cos of 2 pi fct plus 4 sin 2000 pi t, where fc equal to 10 megahertz. Then first question, determine the average transmit power. Second question, determine the peak phase and frequency deviation. Third one, is this FM or PM signal? Explain. Then U of t equal to 100 cos of 2 pi fct plus 4 sin of 2000 pi t, fc equal to 10 megahertz, average transmitted power P equal to AC square by 2 or AC square by 2 r. Here R equal to 1 ohms. Therefore 100 square by 2 into 1, default R equal to 1 ohms equal to 5 kilowatt. The second question is, determine the peak phase and frequency deviation. U of t equal to 100 cos of 2 pi fct plus 4 sin 2000 pi t. S angle of t equal to AC cos of 2 pi fct plus phi of t. Peak phase deviation delta phi equal to modulus of delta phi max, that equal to 4 sin 2000 pi t max. Delta phi equal to 4 radians. Peak frequency deviation delta f equal to 1 by 2 pi d phi of t dt modulus 1 by 2 pi 4 into 2000 pi cos 2000 pi t, 4000 cos of 200 pi t, that is nothing but 4000 Hz. It can be visualized as both FM and PM signals. SPM of t equal to AC cos of 2 pi fct plus KPM of t. KPM of t equal 4 sin 2000 pi t. It can be visualized as PM signal with Kp equal 4 radians per volt and M of t equal to sin of 2000 pi t. SFM of t equal to AC cos of 2 pi fct plus 2 pi kf integration of minus infinity f of t m of t dt. 2 pi kf into integration of minus infinity t m of t dt equal to 4 sin 2000 pi t. 2 pi kf m of t equal to 4 into 2000 pi into cos of 2000 pi t. Kf m of t equal to 4 into 1000 of cos of 2000 pi t. It can be visualized as FM signal with Kf equal to 4000 Hz per volt and m of t equal to cos of 2000 pi t. Question below 1b. A unity feedback counter system has the open loop transfer function g of s equal to k by s of ts plus 1. The system is critically damped and the steady state error is 0.5. When unit ramp input is applied, find out the natural frequency of the system. Then we can write it as g of s equal to k by s into 1 plus s tau. System is critically damped, zeta equal to 1, ess equal to 0.5,
input m applied is ramp, omega n equal to how much, characteristic equation 1 plus g of s equal to 0, 1 plus g of s equal to 1 plus k by s into 1 plus s tau, that equal to characteristic equation becomes s square by plus s by t plus k by t. On comparing with standard equations order s square plus 2 zeta omega n s plus omega n square, we get 2 zeta omega n s equal to 1 by t, omega n square equal to k by t, omega n equal to root over k by t radians per second, 2 into 1 into omega n equal to 1 by t, omega n equal to root k by t. From 1 and 2 we get omega n equal to 1 by 2 to equal to root k by t, that t equal to 4k t square. Okay, now kv equal to limit s tends to 0 s into gh of s, kv equal to limit s tends to 0 s into k by s into 1 plus s tau, kv equal to k by 1 equal to k, ess equal to limit s tends to 0 a by 1 k, a by kv equal to limit s tends to 0 1 by k, 0.5 by 10 equal to 1 by k. From equation 3 we get t equal to 1 by 4 into 2 equal to 1 by 8. From equation 2 we get omega n equal to root over k by t, omega n equal to root over 2 by 1 by 8, that equal to omega n equal to 4 radians per second. With respect to cache memory organization, describe the importance of cache addressing modes considering physical address cache, virtual address cache, and aliasing problem. Write a block schematic depicting memory hierarchy or a shared memory multiprocessor. Importance of cache addressing models. When a CPU generates physical addresses, the access to main memory proceeds with access to cache. Data is checked in cache by using the tag, and index are set bits as shown in the figure below diagram. Such cache where the tag and index bits are generated from physical address is called as physically indexed and physically tagged cache. When there is a cache hit, the memory access time is reduced significantly. Average memory access time equal to hit time plus miss rate into miss penalty. Here hit time equal to cache hit time equal to time it takes to access a memory location in the cache, miss penalty equal to time it takes to load a cache line from main memory into cache. It's in today's system CPU generates a logical address also called virtual address for a process. When using a PIPT cache, the logical address needs to be converted to its corresponding physical address before the PPT cache can be searched for data. This conversion from logical address to physical address includes the following steps. First one, check the logical address in the TLB translation. Look aside buffer. If it is present in the TLB, get the physical address of the page from the TLB. If it is not present, access the page table from physical memory and then use the page table to obtain the physical address. At all this time he adds to the hit time, hence hit time equal to TLB latency plus cache latency. TLB latency plus cache latency. See the double of the tag index offset. Okay, now virtual address is connected to TLB, that is called check in TLB, that is connected to next PIPT cache, which is nothing but physical address if TLB hit. Next data to CPU from TLB. If TLB miss read page table, then if cache miss read from main memory. That are the two caches. Limitations of PIPT cache. This process is quite sequential, hence high time, not ideal for inner level caches. Data cache is accessed frequently by any system and TLB access for data every time will slow the system significantly. Virtually indexed, virtually tagged cache. An immediate solution appears to be virtually indexed, virtually tagged VIVT cache. VIVT cache directly checks the data in cache and fetches it without translating to its physical addresses, reducing the hit time significantly. In such a case, the tag and index will be a part of the logical or virtual address generated by the CPU. Now the address generated directly by the CPU can be used to fetch the data, reducing the hit time significantly. Only if the data is not present in the cache, TLB will be checked, and finally after converting to physical address, the data will be brought into the VIVT cache. Hence the hit time for VIVT cache hit time equal to tag index offset virtual address. If present in cache, that is hit, then VIVT data to CPU. If not present in cache, then check in the main memory. Limitations of VIVT cache. The TLB contains important flags like the dirty bit and invalid bit, so even with the VIVT cache, TLB needs to be checked anyways. Lots of caches misses on context switch, since the cache is specific to logical address and each process has its own logical address space, so two processes can use the same address but refer to the different data. Virtually indexed physically tagged cache VIPT. The VIPT cache uses tag bits from physical address and index as index from logical or virtual addresses. The cache is searched using the virtual address and tag part of the physical address is obtained. The TLB is searched with the virtual address and physical address is obtained. Finally, the tag part of physical address obtained from the VIPT cache is compared with the physical address tag obtained from TLB. If they both are same, then it's a cache hit, else a cache miss. Else a cache miss. Next, tag index offset virtual address, index of VA, tag part of a physical address, compare tag cache like this it will be there. Okay, now next question. For an air-filled coaxial transmission line, The outer radius of the inner conductor is 1 mm and the inner radius of the outer conductor is 4 mm. The outer conductor thickness is 0.6 mm and all conductors have conductivity sigma equal to 1.6 in 10 power 7 Siemens per meter. Find the inductance L and capacitance C per unit length. What will be the resistance per unit length at an operating frequency of 2.5 GHz? The value of epsilon naught equal to 8.854 into 10 power minus 12 farads per meter and mu naught equal to 4 pi 10 power minus 7 Henry per meter. Given data A equal to 1 mm, B equal to 4 mm, T equal to 0.6 mm, sigma equal to 1.6 in 10 power 7 CS per meter, Siemens per meter. Inductance per unit length L equal to mu by 2 pi natural log B by A, mu by 2 pi natural log B by A, L equal to mu by 2 pi natural log B by A, L equal to mu by 2 pi natural log B by A, L equal to 4 pi into 10 power minus 7 by 2 pi natural log of 4 by 1 equal 0.277 micro Henry per meter. Capacitance per unit length C equal to 2 pi epsilon whole by natural log B by A, C equal to 2 pi epsilon whole by natural log B by A. Resistance per unit length R equal to 1 and numerator part denominator part 2 pi delta sigma C into 1 by A plus 1 by B. Delta equal to root over pi f mu sigma, root over pi f mu sigma. Okay na, that is called. Then R value substitute chestam. Design 4 to 1 mux using domino logic. There will be M9 domino logics. Dominos means which will progressively transfer. 1 by F. A silicon PIN photodiode is an optical receiver. This is a peak optical power at 1300 nanometers. The diode has a quantum efficiency of 50% and delivers electrical power to a load of 5 kilo ohms. If the diode receives a peak power of minus 30 dBm, calculate the thermal noise and short noise. If the bandwidth of operation is 8 MHz, the dark current value is equal to 5 nanoamperes. E equal to 1.6 into 10 power minus 19 coulombs. H equal to 6.625 into 10 power minus 34 joules second. C equal to 3 into 10 power 8 meters per second. Kb equal to 1.38 into 10 power minus 23 joules per Kelvin. Given that lambda equal to 1300 nanometers, eta q equal 50% equal to 0.5, RL equal to 8 kilowatt, Pin equal to minus 30 dBm, B equal to 8 megahertz, ID equal to 5 nanoamperes, Pin equal to minus 30 dBm, minus 30 dBm equal to 10 log Pin by 1 in 10 power minus 3, 10 power minus 3 equal Pin by 1 in 10 power minus 3, then Pin equal to 1 in 10 power minus 6 watts, T equal to 20 degrees centigrade, that equal to 290 degrees Kelvin. Room temperature, the thermal noise in the load resistor is given as I suffix T square equal to 4kTb by R suffix L. 4 into 1.38 into 10 power minus 23 joules per Kelvin into 290k into 8 into 10 power 6 by 8 into 10 cube. IT square equal to 1.6008 into 10 power minus 17 A square. The total short noise is I suffix S square equal to 2EB into I suffix D plus I naught. The I naught equal to eta q, eta suffix q, P suffix in E by H into F. Eta q P in E into lambda by H into C. IS square equal to 2EB into ID plus I naught. 2EB into IB plus I naught. E means charge of the electron. 1.6 in 10 power minus 19. A zero Gaussian noise N of T has a power spectral density Sn of F as shown below. Then 0 F naught by T N naught by 2 Sn of F minus F naught దగ్గర ఒక స్క్వేర్ వచ్చింది, F naught దగ్గర స్క్వేర్ వచ్చింది 2b. ఓకేనా. A zero Gaussian noise N of T has power spectral density. Plot the power spectral density in phase and quadrature components of N of T. 10 marks. Power spectral density of 0 mean Gaussian noise N of T is given below. Okay na. Minus F naught, F naught. Maximum amplitude is N naught by 2. Bandwidth is 2b. PSD of its in phase and quadrature components will be Sni of F equal to Snq of F equal to Sn of F minus F naught plus Sn of F plus F naught minus b less than or equal to F less than or equal to b. 0 otherwise. That means minus b to b ఒక రెక్టాంగులర్ డబ్బా వస్తుంది. యాంప్లిట్యూడ్ ఆఫ్ N naught by 2. The graph is F, x axis F,
y-axis Sn of f minus f naught. At 2 f naught there will be 1 square type. ఓకేనా. నెక్స్ట్ y-axis లో Sn of f plus f naught. ఓకేనా. పవర్ స్పెక్ట్రల్ డెన్సిటీ అనేది వస్తుంది సేమ్ మైనస్ బీ టు బి ఎన్ నాట్ బై 2, ఇక్కడ మైనస్ 2 ఎఫ్ నాట్. ఎస్ఎన్ఐ ఎఫ్ఎఫ్ ఈక్వల్ టు ఎస్ఎన్ ఆఫ్ క్యూ ఈక్వల్ టు మైనస్ బీ టు బి ఎన్ నాట్ 0. Gaussian noise n of t can be expressed in terms of its in-phase and quadrature components as n of t equal to n1 of t cos 2 pi fct minus nq of t sin 2 pi fct. The envelope of n of t is r of t equal to n of t equal to root of ni square of t plus nq of square of t. Probability density function of r of t is fr of r equal to r by sigma square e power minus r square by 2 sigma square, r greater than or equal 0, 0 otherwise. Since mean of n of t is 0, mean of ni of t and nq of t also 0. So that sigma square equal to msq equal to 2 n naught b. Here fr r equal to r by 2 n naught b into e power minus r square by 4 n naught b for r greater than or equal to 0, 0 otherwise. Probability density function of r of t is Rayleigh's distribution function. X-axis 0 to r, y-axis fr of r. Next 2 b, a control system is represented by the signal flow graph shown below. Okay na. R next node ki r ki 1 వస్తుంది, next node ki ఈ node ki k3, next k1, next 1 by s plus 1, next 1 by s square, next 1, next 1, next k1 minus k2 minus 5 minus 1. Determine the overall system gain C of s by r of s if k1 equal to 1, k2 equal to 5 and k3 equal to 5 for 10 marks. Okay na. C of s by r of s equal to how much means if k1 equal to 1, k2 equal to 5 and k3 equal to 5, forward path k3 k1 by s square into s plus 1, loop L1 equal to minus k3 k1 by s square by s plus 1, loop L2 equal to minus k1 k2 by s plus 1, L3 equal to minus 5 by s square into s plus 1, number of non-conditional touching loops equal to 0. C of s by r of s if you calculate you will get sensitivity s suffix k1 prefix t at omega equal to 0 equal to how much means C of s by r of s equal to 5 k1 by s square plus s square and so on. Equation you will get. Okay now equation you will get then s k1 of t means s suffix k1 pi t equal dou t by t by dou k1 by k1 equal dou t by t into k1 by dou k1. S k1 t equal to dou t by dou k1 into k1 by t. At s equal to 0, capital T equal to 5 k1 by 5 k1 plus 5, s k1 of t equal to 5 k1 plus 5 by 5 k1 plus 3, s k1 t equal to 0.5.